Okay, so we've talked about the cardiovascular challenges. Now we're going to talk about the respiratory challenges. So we've got two main outcomes, and the outcomes are going to be the exact same. At least the second one's going to be the exact same for the other three lectures. But to start off, we need to identify the four challenges. So we've got low oxygen, high CO2 in the venous blood. We've got high blood flow, which results in high vascular pressure, or pressure inside the pulmonary capillaries, which is less than ideal. We've got increased blood flow that also leads to reduced diffusion time. And then we've got increased ventilation, which means it costs more to breathe, okay, because we're working harder. So let's focus on this first one. So I've got low oxygen, high CO2 in our venous blood. So the job, or what we need to do, is we have to protect our alveolar oxygen and CO2. Okay, so how do we do this? Now, first of all, I want you to look at this figure here. So we've got intensity on the x-axis in terms of percent VO2 max, and we've got pressure on the y-axis. Notice that arterial oxygen stays relatively constant through max exercise, maybe even increases a little bit. However, alveolar oxygen actually increases. Okay, so why is that the case? Well, to start off, you got to remember that when we start to exercise, we not only do we lower oxygen, but we increase the amount of CO2 and the hydrogen ion that's in our bloodstream. This actually facilitates a right shift, which makes it easier to unload oxygen. But this isn't good because in my tissues, I want to get rid of oxygen, or I want to unload oxygen to my tissues so it can use it. And so what happens is we're able to pull more oxygen out of the bloodstream, and this results in a lower oxygen in the blood that's going back to my veins, or through my veins back to my right side of our heart and my lungs. Okay, so quick review of carbon dioxide. We can transport it as bicarb. It can be bound to hemoglobin. It can dissolve in plasma. And when we're at rest, we produce approximately 3 milliliters per kilogram of body weight per minute of CO2. So typically it's about 200 to 250 mils of CO2 per minute. At exercise, that 200 to 250 can increase up to 4 to 7 liters a minute, depending on the intensity and the size of the person, right? So I'm going to, like I've talked about Morgan. Me and Morgan, I'm much bigger than Morgan, even though she's a much better runner than me. Odds are I'm still producing more CO2. So when it comes to determining the amount of oxygen in our alveoli and CO2, we've got these complicated equations. And actually, oxygen's a little more complicated. And so I just want to go through this. If I have you calculate anything on the exam, I will give you this equation, so don't worry about that. So FiO2, that's just a fraction of the inspired oxygen. In other words, what percentage of the air that you're breathing is oxygen? Okay, this is usually almost always about 21%, unless you're like doing a study or something. Okay, so that's 0.21 times the barometric pressure. So at sea level, that's 760. And then you have to take into account the pressure of water. We actually humidify the air. We completely saturate it with water in order for gas exchange to occur. And that number is normally 47. Again, not anything I'll expect you to know or remember. I would give you this information. But we talked about that a little bit with the oxygen cascade last week. And then we subtract the arterial CO2 and we divide that by RER, right? And so this part here is about 150. CO2 is normally about 40. RER is 0.8. 40 divided by 0.8 is actually 50. So we go 150 minus 50. That gives a typical alveolar oxygen of about 100. CO2 is a lot easier. We just take the amount of CO2 that we're producing and we divide that by alveolar oxygen, multiply that by a constant. Much, much simpler. Okay. So look at what's going on here with this figure during exercise. And so notice that when we're in this orangish color, that's when we're exercising. And so what happens to our breathing? Well, it takes a little while for us to ramp up, but eventually we hit steady state. And so during light exercise, we might be breathing at 60 liters, moderate 80, heavy 100. Okay, and all this is minute ventilation equals tidal volume times frequency. So at rest, 0.5 liters per breath times 12 breaths per minute gives us 6 liters a minute. Remember, this is air, this isn't oxygen. At max exercise, we might be at 2.5 liters of air per breath times 50 breaths per minute, 125 liters. It's important to know that we're never breathing as much as we possibly can. We can do a test that's called a maximal voluntary ventilation test, where we just have people breathe as much as they possibly can over a short period of time. And when people do this, they can get in excess of 200 liters, or really like 10, 20, 30, 40, 50% more than what they're doing during maximal exercise. You'll never breathe as much as you possibly can. Okay? And so when we exercise, it's interesting is that we've got these two different phases. We've got hyperpnea and hyperventilation. Now, hyperpnea, if you recall from your physiology class, that's just where we increase ventilation to meet metabolic demand. And how does this happen? Well, we think it's due to the fact that we increase CO2, decrease oxygen, decrease pH. And so what we think happens is before you exercise, your brain talks to your brain and says, hey, we're going to be exercising, so we need to breathe more to compensate for this. Once you start exercising based on the amount of CO2 you're producing, you kind of fine tune and you match so your alveolar ventilation is such that you're getting rid of as much CO2 as you're producing. So we've got a positive component, positive feedback loop component, and a negative feedback loop component. Okay, but during hyperpnea, your CO2 stays constant, even though your ventilation's increasing. But notice we get to this hyperventilation state. Okay, when we start to hyperventilate, our CO2 actually drops. Okay, and this is dropping to counteract our pH. Okay, because our pH is also dropping, or has also dropped due to the hydrogen ion production. Okay, and so we call this exercise hyperventilation. And the reason that this happens is we produce hydrogen ion. Okay, and when we produce that hydrogen ion, we become acidic, and to counteract the acidity, we breathe out more because CO2 is an acid. And so this causes a metabolic acidosis, and so we compensate via the respiratory system because we're trying to get rid of excess CO2 to bring pH back up to normal. This is associated with a rise in lactate because remember, if we got high hydrogen ion concentration, in order to get that hydrogen ion out of the muscle cell, we create lactate, and also when lactate leaves, it brings a hydrogen ion out with it. So, here are your 3 questions or 3 things hopefully you can do after the end of this lecture.